of the day, Mr. Kesava Prasad, is the founder director at VerifygnTech Pvt Ltd. He has around 20 years of experience in industry, having worked with companies like Insolvers Technologies, Red Invent Technologies, HIM Robotics LLP, etc. He is an expert in complex mechanism design and analysis, robotics, machine vision, and so on. He has developed a full-scale animatronic humanoid for entertainment industry. He holds a bachelor's degree in mechanical engineering from College of Engineering, Trivandrum, and master's in machine design from IIT Madras. I request Mr. Kesava Prasad to deliver his. Thank you.
Yeah. Thank you, Sananda Kumar. Hello. Okay. Good evening, everyone. So hope you're all having some background. And I mean, how is the background of this audience? I just want to know all are from which branch.
It's a mixed background, people. So students are also there from different branches.
Okay, fine. From different branches. Okay, fine. Right. Good. Okay. So basically, this normal robotic talks will have a lot of theory and stuff like that. So here I have very limited theory. In fact, there is no theory at all. It's basically about the practical side of robotics. That's what I'd like to cover, and also some myths around this robotics. So that's what I'd like to basically address. And there are some areas which are not really, you cannot call them robotics, but it's in a borderline between actual robot and something else. So those kind of things I would like to, emphasis in this talk. So specifically, I'm looking at the challenges, what kind of challenges you have, what kind of skills you require as someone who is venturing into robotic systems. Okay. And nuances, when I say nuances, there are small things which, trouble a robotic engineer. So these are the specific things which I'd like to cover. And okay, so if you ask what is the definition for a robot, this is a typical kind of definition which you can say. Something which is autonomous, which exists in the physical world, and which can sense and act. Okay, so what I was trying to tell is like a definition for robotics, and see these are typical words which now we hear, especially these autonomous robots, self-driving cars, self-driving trolley, so many things we hear now. So that's why I specifically want to emphasize on this particular terminology called autonomous. So autonomous is, as you all know, it is something, some concept where you can make decisions like human beings. So that's a concept of autonomous. And sense, of course, is to take sensing data from the surrounding. It could be in the form of light, could be in the form of sound, etc. And of course, actuators should be there to move this robot, either through in the form of wheels or linkages, etc. So basically, the main concept which people have, especially people who are coming into robotics in the last maybe 5 years, all of them think that robots are autonomous. But there are in fact, there are a lot of robots which are not autonomous. You can do a lot of stuff even without making your robot autonomous. I can give you a simple example, right? If you look at an autonomous robot carrying some food to people in a hospital. See, this can be done in two ways. One is you can have a complete typical autonomous system where you have a 3D vision camera. It can map the surroundings. Then you do the navigation, give it the navigation system so that it can move around autonomously. It will know exactly where it is. So all sorts of sophisticated kind of thing is possible. But the same thing can also be achieved by having a simple markers along the line where the robot is moving. That will also serve the purpose. If you are sure that your path of the robot is going to be fixed, then in fact there is no need to make it autonomous. Making it autonomous is, it's a fancy thing that to have a feeling that I've done an autonomous robot. But ultimately, see, for a end user, he or she only expects the end result. Whether the robot is autonomous, whether I have used SLAM algorithm, I have used Kalman filters, no one is going to care. Only thing they care is my robot should move from point A to point B, and that too through the intended path without hitting any obstacles. That's exactly what an end user require. So this is where techies, especially being I also during my early part of career, I used to be more of looking at technical stuff rather than the user part. So basically, you try to look at what the user needs and then design the robot. I mean, design the robot. So if that is the case, actually, you will not be too much bogged down by this technical stuff, algorithms and stuff like that. I have to move from point A to point B, or pick path A and move it from A to B. So there you need not require any sophisticated algorithms to run, and the computation, all those things can be minimized. So that's the reason why I'm specifically mentioning this autonomous. So many people tend to make autonomous vehicles, self-driving cars. It's all fine. I don't say it's not good, but there are a lot of other things which can be solved, things which can be solved even without making your robot autonomous. That's the point which I'm trying to drive. It's not that you should not make autonomous, but there are a lot of areas where you can have simple robots do the stuff. Okay, now coming to the type of robots, you have humanoids. Humanoids, you can say, as the really the advanced level. In the robotics, you can say it's quite advanced in the sense there are a lot of things to be considered. It will have vision. It will have balancing of the robot body. So many things come into play. So that's why they are considered humanoids. Then wheeled robots, of course, a lot of people are doing it now. And service robots, social robots, all these are all kind of a subset of wheeled robots, I would say. And I'll give some examples as we go. And of course, industrial robots, this is the area where we normally, in my personal experience, is mostly towards industrial robots and a little bit of service robots. And there is something called quadrupeds, which also will basically four-legged robots. So that's another category. And of course, these are self-driving cars. Self-driving cycles you might be hearing for the first time. Actually, to be frank, there is nothing like a self-driving cycle, but actually, it's a kind of concept which is quite interesting to see. So we'll see that one by one. Okay, this is all this. I mean, what you see on the screen, all of them are actually some kind of service robot. The left, second, and the three. These three are actually service. You can fall into the category of service and wheeled robots. Whereas the rightmost one, this is actually a typical industrial robot in a factory, and the left one is as you all know, it's a Honda's humanoid. It's supposed to be a very advanced robot from Honda. Okay, so now, so this gives you some idea of what this is. This particular robot is called Pepper robot. It's from Japan. There's a company called SoftBank. So in fact, I was in Japan for some time to work on this particular robot, which you see on the right and bottom. It's a type of service robot. So I was there for around 3 months. Basically, my role was to do some packaging of this robot. Especially, there are a lot of items inside this robot. There are around 3 cameras, then so many sensors, motors, and all stuff. So my role was to package everything into this small space. This whole size is around 250 by 250, and this floor space is, I mean, the floor ground clearance is only 25 mm actually. So that was the thing. So, and this is a quick video of a self-driving car. This car is from Google.
Today, we have something extra special for you guys, and you guys will be some of the first people outside of our team and outside of Google to ever drive it.
Oh, there it is. Oh, isn't that cute?
Go ahead and buckle up.
Okay, Eddie, here we go. All right, Tommy, let's go. There's no steering wheel in the way.
It was a big decision for us to go and start building our purpose-built vehicles. And really, they're prototype vehicles. They were a chance for us to explore what does it really mean to have a self-driving vehicle. But in the small amount of time we've been working on it, we have functional prototypes, and it's exciting.
It's really cool. It was like really kind of a space age experience.
Okay. We're like, please. You said relax. You don't have to do nothing.
Okay. So this again, this as I said before, this is a self-driving cycle. It's a concept actually, basically how it will look like if your cycles become self-driving. So it's interesting to see, and probably you can get a lot of ideas from this.
The Dutch cycle more than any other nation in the world, almost 900 kilometers per person. But that also means we have 350,000 bike-related injuries. Now imagine that we would make biking safer, smarter, and easier by applying self-driving technology to bike.
We tell our self-driving bike to figure out where it is, what's around it, what will happen next, and what it should do. We leaned on Google's expertise in self-driving cars, but we had to adapt the technology to work on a bike. We decided to add 2 additional features. First, you can request the bike to pick you up wherever you are, and we developed a comfort mode, adjusting the pedals to a perfect resting position.
I think the self-riding bike could really give a boost to the economy because people could also work on their bicycle. You work in your office, you work in your home, you work in your car. You can even work on your bike.
I have so much more time. My kids love it. They're just free. They can go anywhere they want, anytime they want. It's amazing.
At the Fietsersbond, we feel that this is the big.
Okay, the thing I want you to notice in this self-driving cycle is the initial part where they show someone is trying to push the bicycle and it's not falling. But in fact, there is a product, a company which has developed something in India actually for motorbikes, where to make the motorbikes safer, they have devised some technology so that the motorbikes do not fall down. I mean, if there is some kind of imbalance coming, still it will stay in balance. So that technology actually people have tried out, and this particular, I think, company has been successful to some extent. So in a way, this could be a reality soon. Okay, this is yet another type of robo, which is again not normally you don't see these kind of robots. This is a legged robo. So basically, this is done using basically the pioneers of this. This particular robo is from MIT, and based on the DARPA Defense Fund, they developed these kind of robots, and it's called Cheetah. So you'll see the. So what you can see here is it's actually there is a laser sensor and a camera which actually will be looking at the distance and the height in real time and do calculations. That's what they're showing here. So the calculation happening behind. So what you see is now the robot is with harness, and then next you can see that it is without harness. They'll be doing it. Okay, that's a complex piece of hardware actually. So you can imagine how sophisticated the system would be. Okay, now we are moving into another area which is called as animatronics. Very few people have actually heard about this term. I don't know how many of you have heard this, but it's a very an area where there's a lot of impact and there's a lot of interest. Many people who are artists. There are a lot of engineers who are also artists. So this is an area where you can actually try out. So animatronics is a technique of making and operating lifelike robots, typically for entertainment. So what you see on the screen is nothing but the Jurassic Park dinosaur. So it's actually many people think that this dinosaur was made as a graphic, animation, but it's not only animation. They have actually built a full-size robo like this with a lot of linkages, and this whatever you see as an external is actually using silicone, silicone material. They have actually built the dinosaur texture in the silicone, and then the whole thing is covered over a skeleton, and there are a lot of hydraulic systems going inside this, and actually a lot of wires come out. So that is where they use graphics. Whatever wires and cables come out, they actually remove that in video editing. But otherwise, the whole thing is actually moved by joysticks. We can see how it is done in a video later. So normally, it's called puppetry. Puppetry, what is puppetry? Where someone will be using joysticks or some kind of control to move some kind of mechanism. So it is something like that. So instead of actors, there will be puppeteers. Maybe more than 1, 2, or 3 people will be moving. One will be moving its head. Another one will be moving its limbs. So combined thing will be shot on a camera, and you will get that effect. So that's basically what they do. But the major difference which you see in these kind of things is that there is no intelligence as such, which you expect in a typical robo. It's basically a mechanism, but plus puppetry. So it has been used in a lot of Hollywood movies. This is actually from the Jaws movie. So you can see the internals. So a lot of skeleton, a lot of structures, skin, extra. It's an area where you can learn a lot about materials. If you try to do some project in animatronics, you can learn a lot. Actually, it's not only engineering. You need to know about art. You need to know how to make molds. You need to know how to work with different materials. For example, the material used for the eyes is a special kind of acrylic called dental acrylic, and polishing that acrylic. So many things are there. It's a vast area, very interesting also. So we'll see a quick video on that. See, everywhere throughout this video, you can see the actual how it looks like in the film and what is the behind the scenes things happening. So the whole video is something like that. So what you see now is actually the mechanism, and the corresponding in the movie. This is what you have seen. Sorry. This is exactly what I was telling about puppetry. So as you can see, people are using joysticks. Okay, so that is animatronics actually. So, and this is a kind of this is again an animatronic humanoid. Again, I was part of this. This was actually done for the Magic Planet in Trivandrum, Gopinath Mudgat's Magic Planet. So this actually this is a project where I happen to work a lot in electronics as well. So I learned electronics during that time actually, and in fact burned a lot of resistors and capacitors. And in this process, I also learned a little bit of electronics. Anyway, so this actually a kind of animatronics, because they're here. We have done some face molding. Actually, this face was initially done to resemble Stimmadugad, and finally, based on his request, we modified it. And this was done using silicone, and the hair actually, this is actually the pre-finished thing before finishing actually. So this whole face was done using silicone, as I said. But to make this face, we actually made a mold of the whole head that was done in a special kind of clay. And using that clay as a master, we created a mold in plaster of Paris. So we got the negative of the face. So into that negative mold, we poured silicone actually, and we got this face. So this face is nothing but a skin, so which will only cover from the front to the middle of the ear. So ear plus this face, we combine together into a single thing. And to make it stiff, we have provided a shell like this. What you see, this white color is the shell on top of which the mask is placed. And the hair, again, we have ordered the hair based on a photograph. We gave the photograph to a person in Chennai. So they are people who make wigs for artists in film industry. So to the same people we gave this, and they made the actually hair. So this wig is not the regular wig which you find in normal fancy stores. It's not that. It's actually a bit expensive, and this is done using real hair. And finally, the whole body was made, and I use a lot of help from a lot of artists, sculptors, and again, this whole thing was driven using cables actually. So the whole activity of this humanoid was to sit and stand. Normally, it will be in sitting position. From there, it will stand up and start greeting the visitors. That was the idea actually. It was a tough job, even though there is no intelligence, but there is a lot of other things we had to consider, like the balancing of the whole thing, and so many other things was there. Okay, so if you are interested in animatronics, there are a lot of courses. In fact, now you can do online also. How to do molding, how to make faces of creatures, all those things you can learn online. So basically, in robots to resemble characters and animals in real life, then silicon is a major component. I mean, it's a most important part in any animatronics project. Of course, expressions and movements done by puppetry. These are some of the essential things which you do see in animatronics. And of course, a lot of mechanism design is required to make the whole thing look realistic. The movement has to be realistic too. That is there. So it's a good area where if you are a mechanical engineer and if you are interested in some kind of artistic stuff, this is a good area to be. Okay, now we'll go to the real robotic systems. So technically, you can say a robot consists of a physical body, actuators, sensors, and a controller. And there are typical category based on robot behavior. You can say the basic thing is a sense and act. So if you look at the examples, the typical industrial robot which you see in factories, they fall into the category of a sense and act. They are simply pre-programmed robots where you will program movement path, and it simply keeps on repeating it based on some signal. That's all it does. But that it does that quite fast and quite precisely. That's exactly what is required from an industrial robot. You have to pick for example, a door frame or a door of a car and position it exactly, and some other robot will come and start doing the welding. So there you will require a lot of precision, a lot of speed, limited vibration. So there the challenge is different. Whereas if you come to the hierarchical kind of thing where you have to sense, plan, there is another kind of stage which is called plan. So there is some kind of intelligence which is happening. So in the case of hybrid, you can simultaneously do all this instead of having a linear movement. So here, this is simultaneously, this is doing the sensing, planning, and acting thing. This is much more complex actually. Probably your autonomous robots all fall into this category. And in autonomous itself, if you have a slightly less complex case, you can even think about this serial fashion. You sense, you plan, act, sense, plan, act, like that. Whereas if it is quite complex, then you will have to do this simultaneously. Okay. Now, example of a reactive robot. It's a typical industrial robot which I will be showing you. So here I'd like to look at one important thing in this reactive robot. If you see, there's a lot of fencing you can see wherever you have these kind of large industrial robots. So this is actually, in a way, it's a negative side of using industrial robots, where the reason is, since these industrial robots are all a reactive nature, it doesn't have any kind of intelligence. So even if a human being comes in its way, it doesn't care, it simply hits. And there are cases where few people have died because of this robot movement, having gone into the area of the robot movement, and this kind of accidents have happened. So that is one for which now there is a new category of robots which are coming up. It's called collaborative robots. I'll show you that also. So this is just to keep in mind, to get an idea of what the fencing means. Okay, so that gives you an idea of a typical reactive industrial robot. So as I told you, industrial robots are confined to a particular space. If you go to any automotive factory, or any, for that matter, any kind of heavy engineering factory, you can see a lot of robots, but all those robots will be enclosed in a fencing, a lot of grills and other things, so that no one is able to go inside. And there are a lot of safety measures they take. Like, for example, if someone needs to go inside through the door, the moment they open the door, the whole robot will stop, come to a standstill position. So those kind of safety features people employ whenever they put a lot of robots. And when I say hybrid robots, there is, you can have, it has got this vision, speech, sensors, AI, so many things are there. And as I told you, the social robots and service robots, they are all normally fall into this category of hybrid robots, where it has got motion, it has to plan its movement, it has to have vision to take data, should have sensors like proximity, range, to prevent obstacles, to look at sense the touch, sense force, and in fact it has to even get speech, to have speech recognition. So it goes on like that. So when it comes to skills, as I told you before, if you look at in robotics, you probably require a lot of multidisciplinary skills. It is not that those who have done robotics as a course will know that they learn a lot about electrical side, how to interface with sensors, how to interface with PLC systems, how to interface with microcontrollers. So all these, it's a kind of mixed knowledge you need. It's more than a specific deep knowledge. You should have a more wider knowledge when it comes to robotics. So of course, mechanical. If you are a mechanical engineer, you can actually focus more on the mechanical design part, and then probably little bit of the interfacing part to the PCB design, electronics, interfacing with sensors, and what kind of challenges you face, and so many things. And software people can probably do some AI, computer vision. So it's a combined thing. And normally a typical project might have at least 3 different experts, one in electronics and electrical, another in software, and yet another in the whole mechanical stuff. So it's a combined thing actually. And there are cases where all the 3 are done by a single person or a small team. So all of them will do something like that. So that's also there. Whenever you have smaller companies, you normally have such people. In companies like ours, I have a mechanical engineer. Actually, he does everything. Actually, he does mechanical. He's basically a mechanical engineer. He does mechanical design. He does electronic circuit. In fact, he does PCB design, he does soldering, he connects the sensors, take data. He also writes software. So it's like that. So he get a lot of experience doing that. And when I come to challenges, there are a lot, in fact. So this is the internals of the robot which I was talking to you before. That is this particular robot which you see here. It is the internals of that robot. Okay, now the challenge here was you can see this. My role, one of my tasks was to a suspension system for this robot. So you might be wondering, why do you need a suspension system for a robot? Because if you look at wheeled robots, one challenge is that if it's a plain, completely plain kind of leveled ground, there won't be an issue. But if you have ground levels changing, there are small changes in levels which can actually happen. Then what happens is probably one of the wheels may not be touching the ground. So that might create, some problem with calculation and all. And another challenge is like, especially in European countries and countries like Japan, there many places they'll have wires running through the ground, and your carpet will be on top of that. So a typical problem is when these robots come and hit this particular small ridge, it might be as high as say 10 or 15 mm. So this might pose a problem for a robot to move over that. And it might hit there, and it will simply may not cross it. So these are the areas where you need some additional stuff like a suspension. So my challenge given to me was to put a suspension at such a small space. So I was using some kind of design, something like this, and making it miniaturized. And there I had to do a lot of things. Like I had to put a spring, and I need to find what is the suspension movement, a minimum movement of around 10 mm. At the same time, it should take a particular load. So that's a little bit of mechanism design was there to optimize this for this particular small space. So when it comes to real problem solving, your theoretical part is only a small area where it will help you a little bit. Remaining is about your intuition. And for example, one example I could give you about intuition about stepper motors. So when I tell you about motors, I think I'll give more details about that. Okay, so the mechanical design challenges, normally one of the key design challenge in any mechanical design is vibration. So it's very difficult to identify what exactly is causing the vibration of particular part. So there you might go into higher level of analysis, like you can do a CA analysis to find out where the vibration is occurring and whether I can change the material, where I can change the thickness. So many things you can try out in the CAE level, and then improve your design. And of course, other challenges are like assembly design. When I say assembly design, how to assemble the part. So when it comes to a production level product, you need to assemble your product as fast as you can in an assembly line. So there you'll have to think the principles of assembly, like you should assemble things from the top to bottom, unidirectional assembly. There's a principle in mechanical engineering called unidirectional assembly, where as far as possible, all the parts should be assembled in one direction, one top of the other. So these kind of small things you will have to consider while designing mechanical systems. And another thing is the load and torque calculation. Of course, you should have some basic idea of how to do a load and torque calculation. And this calculation will vary depending on what the type of motion is. Whether the type of motion is only horizontal, the type of calculation is different. If it is if the motion is like a flywheel kind of motion, then the calculation of torque is different. If it is a sliding motion, then the calculation is different. So there are small. It's not all rocket science. It's basically I used to tell people when I take classes, I used to say the calculations if you do for any engineering, problem solving, mostly you need not know anything more than your +2. All the calculations which you do is up to +2, nothing more than that. You don't need a PhD to do in fact, to design robots. Unless you are doing very complex materials, nanotechnology kind of stuff. Unless you are doing that, you don't require maths or physics knowledge more than a +2. But you should know the fundamentals, of course. So that's basically the idea. And another thing is structured designs. As I told you, structured design challenge is basically related to vibration. How vibration is coming, you need to solve it. For example, we had one case of, it's not robotics basically, it's basically a cutting machine, a rubber cutting machine, which we had a problem of vibration. And the rubber cutting machine as such is quite simple. That's a rubber bush will be rotating at 1000 RPM, and there'll be two blades coming and doing the cut. So the problem was the cutting is all happening. The problem is the rubber starts vibrating in a very small level, maybe in terms of say 1 mm, but this 1 mm of movement is quite large because the cut itself is only 0.5 mm. So a vibration stroke of 1 mm is quite large for that. So finally we found that the vibration came out of multiple things, not only one thing. One reason was a motor. So we changed the motor and that reduced the vibration. And then the structure on which the motor was placed, so that we found that is creating some issue in vibration. So here it's a kind of, so when it comes to vibration, it's only not only your knowledge of vibration, basics of vibration is may not help you. There you will have to do a lot of practical observation, how we can solve. So of course you can use your basic solid mechanics skills can come into play, but otherwise you should be actually observing your actual problem and then try to find a solution for that. So problem solving, of course, is where engineers are put to test. And this is a typical design case which I was talking about. In my case, the suspension, the mechanism is something similar to this. It's not the exact design. Of course, I'm not supposed to disclose the real design. So this is the mechanism was something like this. So the challenge was to reduce this pin to this pin height because the total ground clearance was only 25 mm. And where exactly to put the spring. So these were all the challenges. Selection of spring and the ground clearance, simulate the loads. Even though the loads were small, loads were in the form probably in the level of say 2.5, around 5 kg or so. I mean the loads were small, but still we had to do the calculations to find what is the effect. So we used the MATLAB actually to do the simulation. So we combined MATLAB and SolidWorks actually to do the simulation. So we did the 3D modeling in SolidWorks, and we connected SolidWorks to MATLAB. So that is possible actually. And we did the analysis there. Okay, now coming to motor selection, I told you there are a lot of motors. This is a typical area where fresher engineers, whether it is robotics or not, many people find it difficult to what kind of motor should I select for the particular application. This is a typical challenge people have. And so this, what you see on the left hand side top is a typical servo motor. It's an industrial servo motor. This is actually a hobby servo, which you can get for 400, 500 bucks, which you can use for small, simple, toy applications you can use. And this is slightly powerful DC motor. And this is a geared motor. This is a geared motor. What you see on the front is a gear, and this is a motor. And what you see here is a typical DC motor without any gear. And this is a stepper motor. And stepper motors are all normally people feel that for a precise movement it is better to use stepper motors. But of course, stepper motor comes with its own issues like jerk and jitter. They call it jitter, where the shaft starts vibrating. And there you will have to do things like reducing the step size. But again, when you reduce the step size, there is another drawback. The moment you reduce step size, the torque achievable torque will be reduced by 10 to 15%. So in that case, you will have to select your, for example, if you do the calculation and find the torque as say 0.5 Newton meter, and probably you say, okay, something which 1 Newton meter should be okay for me. So you might select a motor like that. But finally, you find there is a jerk and a jitter issue. So what you will do now, you will try to reduce the step size. When I say reduce the step size, every typical stepper motor will have 200 steps in one revolution. So that means a single step will be 1.8 degrees. So when I say reducing the steps, I can bring it to half steps or 1/4 step. So this 1.8 degree might become 0.9 degree or 0.45 degree like that. So what happens is as you reduce the step size, your movement becomes quite precise, your jitter will reduce. But there's a drawback, as I said before, your torque will come down from 1 Newton meter to say close to 0.5 Newton meter. So which is, and your design torque is 0.5 Newton meter. Now you have a problem. So that is why, that is where you need to do torque calculation, and always take a motor which is slightly more. It's not like it should be 2 or 3 times. So if you need 1 Newton meter, try to take a 3 Newton meter motor, stepper motor. So something like that. So this kind of calculation you have to know. This of course comes only through experience. So these are the kind of challenges people face while working with these kind of things. So it's not only calculation; it's a combination of calculation, experience, and learning from things. And this is again a small set of sensors which I've shown. This is a top, or is a typical IR sensor. And again, when I say IR sensor itself are up to multiple types. It's a typical IR ranging sensor where you get an analog output based on the obstacle in front of it. And this again is a typical ultrasound sensors. Many people might have used this again to detect obstacles, but these two are different. The IR is more precise compared to an ultrasound, because ultrasound, the waves are going in a spherical fashion, so it can detect other obstacles also. Whereas IR sensor normally looks at the obstacle straight ahead. So that's the difference. And what you see on the left hand side here, this is a typical encoder. And what you see here is a force sensor. So these are all typical sensors which you use. And then comes the robot simulation. There are a lot of softwares now available, especially open source. What you see here is a software called VBot, and Gazebo is again what you see in the bottom. And so many other softwares are there. And RAS. RAS is actually a robot operating system. Those who are into robotics know that. But I have a small. I'm slightly not inclined towards using RAS due to multiple reasons. Because for simple projects, RAS is okay, but when it comes to industrial, there are a lot of issues working with RAS. But there is an industrial version of RAS now coming up. Probably that is performing one. But I personally prefer to do robotic projects without RAS. Probably to start prototyping, you can use RAS, but ideally you should use typical, from the scratch kind of thing to do that when it comes to deploying your robot. Because typical issues which come are RAS basically as a software is a bit heavy. So running this whole RAS in an operating system, that it's going to be taking a lot of computational resources. So that will slow your robot. So your robot, if it is going to be working in real time, of course, RAS may not be a good option. But to be frank, I have never used industrial RAS. I am yet to, if someone is using industrial RAS, please correct me. Because, but the normal RAS, I know that it's not that fast. Anyway. And then coming to controller hardware design, this is another area where you require some kind of skill. So I've told you about the mechanical skills you require. Then coming to controller hardware, you should know how to select a particular board, how to select a microcontroller, and on what basis you'll be selecting that. For example, whether you're going to go by the Atmel, Atmega is a typical Arduino level of sensor, microcontrollers, or you're going to the ARM processors. These are all decisions to be made, or you are going to a PIC way. So many microcontrollers are available. So which one you choose again is different. Or are you going to use a typical single board computer like a Raspberry Pi or a Jetson Nano or something like that? So each has its own advantages and disadvantages. We have a lot of experience working with Raspberry Pi. We have developed Raspberry Pi based industrial systems. So we have finally found that many people are attracted to Raspberry Pi. The reason being you can code in Python. It's a good thing for as a beginning, but when it comes to a real application stuff, we have found that Python is slow. But there are, of course, ways to improve Python speed. So finally, we in a particular application, we actually ported our complete Python code into C++. And now the whole system is blazingly fast. Almost you can say 10 to 15 times faster than what it was in Python. But of course, Python was very fast to do the prototyping. We could show results probably in a week's time. That is probably an advantage of using Python. But when it comes to performant code, which has to run faster and without any other kind of issues, then you probably will have to go the C++ or C way. And coming to, again, I told you the control board, the motor driver board. This motor driver board is another challenge which people face. Many motor driver boards will fail after maybe a couple of, say, 100 hours or 200 hours of operation. So how to select a proper motor driver board. Then another challenge is to select a proper power stage. For example, normally for robotics, you might use 12 volt for the battery. And from this 12 volt, you'll have to probably give a 5 volt signal to your microcontroller. Then how to change that? So there you might have to put something like a DC to DC converter. So DC to DC converter, which is available in the market, local market, are not reliable actually. We have tried at least 5 to 6 different types of DC to DC converters until finally we have came to a particular type. So it is actually a challenge. Unless you try out, you won't be able to know. So these are all the challenges coming into the hardware side. And of course, battery selection is another. And one is battery selection, other is to reduce the power consumption. How to reduce my power consumption, like turning off. There are all microcontrollers have something called a sleep mode. So making it to ultra sleep or sleep mode, where the power consumption, current consumption should be in microamperes. Say something like 0.5 microamperes might be the current consumption is in a particular ST micro, ARM microcontroller. And there will be other microcontrollers which will not have the ultra sleep mode. So it all depends on what kind of application you are going to use. So many things you'll have to look at. And of course, vision system design is yet another area which people can focus. Both those who are interested in vision systems, that's an interesting thing. We are working a lot with so-called machine vision systems, not the typical face detection kind of thing. We are mostly working with industrial vision systems, where the requirement is to find defects in manufacturing lines. And so there again, that's again is a special area where we'll have to learn about vision algorithms, image processing, etc. And you also need to do some kind of AI in some cases, where you will use things like CNN and machine learning, etc. And here again in camera, you need to see many people are doing experts in probably writing software for vision system, but many of them lack the skill in selecting cameras. Selecting camera is a very important decision you have to make. What kind of focal length you're going to use. That is another area you should know, whether I'm going to use a 4mm lens or 8mm lens, 12mm lens. What are the implications? How the focal length is connected to the field of view. Field of view is nothing but the area which your robot is seeing. So there is a relation between your field of view and focal length. Larger the field of view, smaller will be the focal length. For example, a 4mm lens can easily see say around 600 mm at a distance of 400 mm, whereas at the same distance we are putting a 12mm lens, your field of view will reduce to 100 mm. So these kind of things, these are all fundamental things, but these are things which you need to learn. And again, lenses are of different types. You can have telecentric lens, normal lens. So many other categories are there. So everywhere, I mean, as you go deeper and deeper into a particular area, you have to learn small other stuff which is normally not in your particular field of expertise. So processing, as I told you, that image processing, and there's a couple of another myth which people have is computer vision and image processing. They are two different things. Actually, image processing is a phenomenon area where you do a lot of algorithms to modify your image, filter your image, change the color, extract the color, do some template matching, undistorting the image. These are all coming into the category of image processing. So, for example, here what you see on the bottom is it's a typical technique called surf, where you're trying to compare two images. So using key points. So you can see this comparing this book and this particular book, they are the same. So it is able to easily correlate this using a particular key point algorithm, which comes with the typical popular OpenCV library. And then comes another skill, which is nothing but the algorithm design. As I told you before, when it comes to robotics, you will have to have algorithm design for selecting the path, moving the robot. So many things are there. And there you have to use multiple techniques, not only neural networks. You will have to use techniques like Kalman filters to predict the next position of the linkage. And you have to do some kind of path planning here to initial point to final point. You have to find the shortest route. There you will have to use the A-star algorithm. So there again, it's an area of computer science work. And then speech recognition, that is another area that's part of the AI. And coming to the nuances, this is the typical nuance, or typical, I would say nuance is nothing but the typical bugging factor of something which is creating a pain for engineers. That is the effect of forces, effect of inertia, jerk, and vibration, as already I told you. And apart from, there is one more thing which I have not included in this, which is called a typical effect of interference. Especially this is very important in the cases of computer vision. We are using sensitive electronic things like cameras and other sensors. So I have a typical experience of using cameras in an industry. We took the camera system to a particular factory where we tried to install this setup, this prototype setup, and tried capturing images. But for some reason, this camera is not capturing. The camera is not working. The same camera, when we bring it to our office, it is working perfectly fine. So finally, after a lot of trials and a lot of digging around, we found that this camera was sitting in a place where there is a high frequency welding happening. So this high frequency welding, of course, will create a lot of electromagnetic interference, and that is affecting the camera. So the moment we took the camera to a different place, maybe slightly away, so it started working. And so for that particular installation, we had to put a lot of shielding for the camera, and such stuff. So these are all things which you probably get only through experience, but I'm trying to say these are all the in and outs of any particular engineering problem solve. And again, in hardware nuances, you have to, as I told before, you should know a typical confusion people have is between the bit level, whether I'm using a 32-bit processor or 8-bit processor, and again, sampling rate. Sampling rate and the bit depth, they are two different things. For example, you are taking some sensor data. How much accuracy should my sensor have? Whether it should be a 12-bit is okay, or whether I should have a 14-bit. So when you say 12-bit, it is nothing but 4096 levels. 4096 levels of values are there. Whereas if it is a 10-bit, you only have 1023 levels. So that's the difference. So suppose you are to take your voltage is from 0 to 5 volts, so it is 5 volt by 1023. That is a resolution. Whereas if it is 12-bit, it is 5 volt by 4096. So you have to decide what is the resolution you need. And this is one thing. And second thing is about sampling. Whether you need 10,000 samples per second or you need 1 lakh samples per second. Again, that is another thing. So this will decide what is the type of microcontroller you should select. And another thing is about the connectors. There are different types of connectors, standard connectors available. The percentage variation. Another key thing is about the percentage variation in the resistors and capacitors. Normal resistors which you get in the market is only accuracy of 10% variation. So this might affect in applications where you have very stringent, analog sampling. This will affect your value. Of course, effect of humidity, electromagnetic difference already I told you, and noise in circuit. So of course, again, software issues, loading OS in various embedded platforms, software driver issues, which we regularly face in many customer, installations. Especially as an advice, I can tell you, try to avoid RS-232 interfacing wherever possible, because we have struggled a lot with the RS-232 connectors, because especially if you are using Windows, RS-232 drivers always create problems. And whenever there is a Windows update, your customer is going to call you and saying your software is crashing. Ultimately, when you go and see, the problem will be nothing but your software driver has been updated. Your RS-232 driver has been updated to something else, and now your software and your hardware is not at all communicating. Now, probably the job is only a 10 minutes job of changing this the hardware settings in the device manager Windows, but again, it's a pain. So these are all kind of experience which you get. Okay, thank you for your patient hearing. Hope I didn't bore you.
Thank you so much for that. Amazing.
Okay, thank you.
So, in between the sessions, we had received some questions.
Okay. Sorry, actually, I didn't go through this your chat. So probably you can ask now.
Yes, sir. I'll go. The first one is related to the animatronics, which you had shown in your slide. Is CGI or animatronics easier or profitable? Right?
Pardon?
Is CGI or animatronics? Yeah, CGI. Or animatronics easier?
Computer graphics. When you say CGI, it's computer graphics you're talking about?
Yes, sir. Yes, sir. Or animatronics easier or profitable?
See, profitable is it's again depends on your how in what scale you do that. See, animatronics of course is a very specialized thing. When you compare CGI and animatronics, I would say that CGI is something which you can start off easily because you only require software basically, and a lot of software is available in the open source world like Blender and all. So it's easy to start off. But whereas animatronics is a tough area, but if you can prove yourself in the animatronics field, it's a good area, I would say. You can probably do both because both are related.
Okay, sir.
But when you say profitable, that depends on even if you are in CGI, you can be not profitable, and so it all depends on the type of work. So that you cannot say. But of course, CGI is easier. That I can say.
Yes, sir. Yes, that's true. And the next question which we had is, sir, could you talk more about the simulations which we can use in industrial robots? As you had said that ROS are not applied in industrial robots.
No, yeah, I mean, for robots, actually, I would say there is something called a software, which is actually a paid version. It's called a RoboDK. It's a paid software, but there is one advantage of one good thing about RoboDK is they have a library of this RoboDK library is available freely to use. So even if your license expires, you can always use the RoboDK library. Only thing, you can't actually use their 3D interface. Their 3D interface is really good, where you can drag and drop. I think they have around 200 plus libraries of industrial robots, ranging from ABB, QCA, Denso, you name it. Any popular brand is there in their library. You can simply drag and drop that robo into the scene, and you can simulate the movement. All those things you can do. But of course, it's expensive. So what you can do is you can take a trial version, play around with, understand, do some simple exercise, and then start using their Python library. So that is one way of using it.
Okay, sir. So,
otherwise, you can go for, if you want, there are other libraries called VBot. And there is something, there's some other libraries also there. I'm not able to recollect the name now. Yeah, it's called VREP. VREP is, I'll type that name here.
Okay, sir.
So VREP is also one, and VBot is another. And you have Gazebo. But of course, all these things are platforms, but you don't get any standard off-the-shelf robots from these softwares. But you can always build a model of that real robo in these softwares with some effort.
Yes, sir. So the next question which we have is, sir, if we are doing a project on robotics, then should we know all the basics of robotics and then start off with it? Or
it is not like that. I would say that no, nothing like that. See, you can always this is a time you can make a lot of mistakes. So I would say that you start doing it. See, my concept of learning: you start doing it, make mistakes, then learn back. I mean, for example, if you try to teach someone mechanisms, theory of machines, it will be a boring class. Instead, what you do is you ask them to make a mechanism and let them fail. And then they'll themselves will feel the interest to learn theory of machines. So that's a concept which I have. So in that sense, you start building something. I mean, start making, let it fail. It's okay. And from there, you start learning. That's the best method.
Yes, so that's true. And the next question is, so when an industrial robot is constructed, are the electronic equipments costlier, or as they have to be more accurate and error-free?
Pardon me?
It's related to when we build an industrial robot, the electronic equipments are a bit costlier.
Yes, that is right. Yeah, because if you look at a typical industrial robot, the robot will be costing you anywhere from 12 lakhs to 20 lakhs. That will be the robot cost itself. And there'll be additional cost of making a fence and so many other things. So a typical robot project will cost you something around 15 to 25 lakhs based on the size and all. So what was your question? I mean,
like, are they costlier? That was the question, and you answered it. Are they costlier? Yeah.
Yeah, they are costly. Of course, they are costly.
Yes.
But there are cheaper alternatives now coming. Many lightweight robots people are building, even in India actually. There are options, yes.
Okay. And two more quick questions. Apart from computational issues, are there any other practical issues with ROS?
I don't think there is any practical issue, but I'm looking at, see, I'm talking, you can always use ROS. It's not that I'm against ROS. You can always use ROS, but the only thing is when your kind of application is so demanding and so real time, in such cases, ROS might fail. That is the only thing I'm telling. It's not that there are a lot of cases where ROS can be completely used. There is no issues. But if your system is going to be quite fast, quite responsive, if that is the kind of application you are looking at, then I don't know whether ROS is the right solution.
Okay, sir.
And again, another thing is to the whole installation procedure. For example, if you are going to deploy a robot, you'll have to install ROS in that system, and then you have to put all the drives, all the other things you have to do. You have to set up the whole machine. So this can be avoided to go the other way around. That's the only thing.
Okay, sir. So we have some more questions too. Sir, is it possible for you to clear all of this, or you could?
Yeah, maybe. What is the other question you have?
The last one is, what about soft robotics, materials and all?
Yeah, soft robotics, basically, that is a kind of a new area. When you say soft robotics, there is another area which is called, I told you about, the other type of robots which doesn't require any fencing, which is called the collaborative robots. It's all cobots. COBOT. I have typed that. Collaborative robots. Now that is becoming a trend in the industry where these kind of robots actually can work along with humans, because these cobots have some sort of intelligence built in, so that even suppose you try to pat on top of or hit on top of on the limb of this robot, it will immediately stop. So if it comes and hits a human being, then it simply stops there. So that kind of robots are called cobots, and so humans and these robots can work very in close proximity. There is no need of any fencing and other stuff. So advantage of these cobots is the total cost of the robot will come down by at least one half. If the other robot is around 20 lakhs, this will be around 12 lakhs, in that range. So cost wise also is lesser. And another thing is teaching this robot is also easier. We can use some code or even Python or C or C++ to program these robots. Whereas industrial robots, which you see in the industry, you have special proprietary kind of software and the code, G code, you have to use to program them.
Yes, sir. So our future is nearing. So we could work with robots too.
Yeah, sure, definitely.
Okay. So I thank sir for this wonderful session you had taken for us. And before closing our session, I would now like to invite Mr. Jen K. Jennings, Chair IEEE JCT, to do the vote of thanks and present our token of love to Keshav sir. Jen, please.
Hello, Jash. Hello, Jash. Am I audible?
Yes.
Yes.
Okay. Good evening to all. So we have reached the end of an amazing and enlightening session. And before we wind up, I would like to extend my few words of warmth and gratitude. It's my privilege to have been asked to propose a vote of thanks on this occasion. Today, we are very lucky to have such an experienced person, Mr. Kesava Prasad, as a speaker of this session. He's an expert in complex mechanism and analysis, robotics systems, machine vision development systems, and many more. Sir, I truly appreciate your willingness to give your time to enrich the lives of young people. The session was really informative and an enlightening one. Thank you, sir. I also request you to receive a virtual memento as a token of our love.
Thank you all for your patient hearing.
Sir, I thank our management who were always supportive enough to conduct our events in an organized and successful manner. I thank our principal, Dr. J. David, manager, Reverend Father Matthew Korankura, and Dr. Mathuguma, IEEE Dean, and also Vice Principal of SJCT for their constant support in carrying out our activities. I also thank Mr. Sabrina G, Vice Chairman, IEEE Kerala section, and also our proud faculty of SJCET for strengthening and empowering us in our ventures. I extend my special thanks to Jisha Ma'am, Chair, and also Vice Chair Nandakumar Sir of Robotics and Automation Society Chapter, IEEE Kerala section, and their team for collaborating with us. Thank you all. Now, I thank our branch counselor, Dr. Arun P, for his support and guidance in our all endeavors. Thank you, sir, for being with us this evening. I thank the faculty advisors of their cooperation for the cooperation in conducting these events. This event would never have turned into a great success without proper planning and execution. We have been fortunate enough to be backed up with a team of very motivated and dedicated EXICO members of IEEE SJCET who worked hard for the success of this event. A special thanks to our design team also. Then last but not the least, I specifically thank the participants who have been the backbone of this event through their active involvement. You guys are the real success of this event. Thank you all.
Thank you, Jen, for those words, and thank you, sir, for joining with us today. Thank you, Jisha ma'am and Nandagoma sir, for all the support and guidance you had given to us. Thank you all participants again.
Thank you all.
Thank you all.